We're at PyData Austin. It's Saturday. Oh, sorry, this is objectionable content. We're at PyData Austin. It's Saturday, December 7th, 2019. This is a talk about the Python object model. My name is James Powell. If you like this talk, you can follow me on Twitter at don'tusethiscode. In fact, you might want to open that up right now because the screen may not be large enough for you to see in the audience. So I've put a teammate link on my Twitter feed so that you can follow along on your computer and watch everything I'm doing on my screen without having to squint at the poor resolution in front of you here. So before I get started with this tutorial, I want to just briefly touch upon why this is a topic that anybody at a PyData conference should ever care about. What we're going to talk about here is almost entirely going to be about how Python works, how the object model in Python works, how design of systems with the Python object model works, and we're going to touch upon almost no scientific computing and absolutely no machine learning, and probably very little data science or anything similar to data science. As an anecdote, I was very recently working with a company that does silicon photonics. And the work that they do is very deeply scientific and very deeply mathematical. However, that work is situated within a production context. They're not doing research for silicon photonics. They're actually going and producing physical pieces of hardware. And so while, as part of that work, they may employ machine learning in order to figure out yield predictions or in order to look at images of the chips and try and figure out if those chips are going to fail or not in production. Fundamentally, they have some kind of production process whereby their design needs to incorporate into some system which can go and produce these chips. There's a lot of production level programming beyond just the analytical side. And as part of my work with them, trying to train some of their scientists to be able to use Python more effectively, we looked at a couple of sample problems that were relevant to them. It turns out, and it was quite surprising to me, that there's very little work in layout and placement for silicon photonics. And while that's not exactly the example that we'll use here, we'll use a much simplified example that might touch or be within spitting distance of that. Fundamentally, in order to do a layout system, you're going to have to figure out how to write a business rule system. In order to write a business rule system, you're going to have to figure out how to use Python more effectively than just writing functions. And so for many of you, in your use of Python as a data scientist or as a machine learning expert, you may have really only gone so far as to write maybe a couple of functions. You might play around with keyword arguments in Python. You might have written a couple of classes, but you've never had to write large system design. And what I'll try and convey to you in this talk is that that kind of large system design is necessary the moment your analytical work gets situated in some kind of business context and somebody needs to do something real with it. For example, to drive some automated testing process, or in order to drive some yield optimization process, your analytical code can't stand alone. And so you have to branch away from just using your NumPy ND array directly or your pandas data frames directly to do some analysis. You have to start building systems and mechanisms around that. Now, I have a very brief agenda for you. We've got about 90 minutes for this tutorial, and I'm not sure how the timing will work out. But I'll spend as much time as I can showing you a couple of things that you may or may not know. This is a pretty novice level tutorial, so there may be some content at the beginning that you're already very familiar with. And then once I show you some things, we'll try some things. We'll work on an example, perhaps together, in order to, that may make use of what we see about the Python object model in order to actually design some kind of system. Now, I suspect that we won't have enough time in the example portion to complete this example. The example that I'll show you in a moment is about modeling simple, linear, planar circuits and automatically computing what the current and voltage at different points are. There's a little bit of mathematical work in there, and we may not get as far as that, but hopefully we'll get just far enough to think about how we would design a tool that could do that using what we see in this first portion. Okay? And so let's get started. So this is me on Twitter. You can see that teammate link there. If you click on it, you'll see something that looks like this. This is the session that I'm going to be working out of. And so if you go to my Twitter feed at don'tusethiscode and you click on that link, you won't have to squint at the screen up here. And also, all the people at home who follow me on Twitter will get to see this talk for free, but they won't get the audio. So they'll have to figure out what we're doing. Now, let's get started. So let's talk about Python objects and the Python data model. And we'll start very simply. I mean, a lot of you are data scientists, and really when we talk about Python objects, the most you may have ever touched upon is maybe a pandas data frame or a NumPy ND array and some dotted methods on it. Instead of saying, instead of from NumPy import sum, you did numpy.ndarray.sum. And you know that there's methods and there's attributes on these objects. We haven't gotten that much further. And a lot of your code, you may just work pretty much almost entirely with the built-in types. And so it may be the case that if we had a simple program that was trying to model like a simple circuit we might start by modeling each of the components of that circle as just a tuple. And when we can see if we do that, we get a simple tuple type, and it has some fields associated with it, and there's nothing too complex about that. Now, when we actually try to interact with that, we have to access the fields of this tuple, and we'll see that that's going to be a little bit unpleasant. We have to use direct field accessing, and it's kind of ugly. It's not clear to us what component 0, 1, 2, or 3 might be if this block of code that's accessing the fields is very far away from this block of code. But, it kind of works. And we might at some points make use of tuple destructuring in order to give names to these fields. So we might destructure this into 4 different variables and then access those variables directly. And that's kind of nice, but we still have this fundamental problem that the tuple, when you destructure it, you need to know the order of the fields themselves. And if this code here is very far away from this code here, it may be very difficult to keep these two in sync. What we might then try is we might try something a little bit fancier. We might say, you know what? I want to be able to access the fields of this object directly. And I want to have some self-documenting behavior here. So instead, I'll use a dictionary. And the keys of the dictionary will be the field. And the values of the dictionary will be the actual value on that field. And so that kind of works. There's nothing too fancy there. When I go about accessing the fields, it's not altogether that difficult. I just use my square bracket indexing for the dictionary. And it's a little bit ugly. It's a little bit clumsy. I have to add square brackets. I have to have these single quotes or double quotes. But it's a little bit nicer than the tuple in that if I were to add fields later, I don't have to go and change all the code that I've already written. And visually, it's a little bit closer to being self-documenting. Now, I might then try something very silly. Maybe, for example, I'm a JavaScript programmer, and I really like how JavaScript, the objects in JavaScript can be accessed using the square bracket syntax or the dotted syntax. So I create something like an attr_dict, and I just override the getAttr, setAttr, and delAttr for a Python object. So it just calls the dict's getItem, setItem, and delItem. And so here, I have effectively the same code as before, except now I can access the fields by name using this dotted syntax, just like I can in JavaScript. Now, this is kind of silly, and please don't ever do this. This is a really bad idea. It doesn't gain you a whole lot, and I don't know why people just really seem to hate typing those extra square brackets and the double quotes. But if you really think about it, you really dive a little bit deeper and you think, is it that silly? It's not really that silly, because if we were to write this as a normal Python object, just a regular class with an init method, and we were to look at that class, we'll see that inside that class there's an attribute called dict with 2 underscores before and after, and it's pretty much the same dictionary as the dictionary above. And that dict object is where it's storing all the instant state. So we might say, you know what, this attr_dict structure, despite being a very bad idea, and by the way, if you try and look up how to write that, there's 2 formulations that you'll see people talk about online. And one of them is a terrible, terrible formulation where you set the dict of the instance to itself, and you end up with potential memory pressure because it has a circular reference. And so when the garbage collector tries to collect this, there's some delay in its collection. And so don't do it at all. But if you're going to do it, use a formulation I showed you above. However, one argument you might make is that it's not altogether that different than how Python dictionaries are actually implemented under the covers. Now, if we try that, one of the things that we might have run across if we've ever done some object modeling in Python is we have some system and we have lots of these kind of resistor objects because we're modeling humongous circuits, and we're seeing that it's using a lot of memory. And it turns out that this formulation of the Python object that has this dict object inside of it, representing all of the instance state, does use a lot of memory. And so we can look at this object and we can ask the sys module, what's the size of this thing? And the sys module will tell us, it's 48 bytes in size. And so it's pretty big for one individual piece of data that really doesn't store a whole lot of information, just some part number, some manufacturer, and just the resistance, presumably in base units and ohms, of this component. Now, if we were to really get a bug about us to try and do some kind of management or some sort of analysis of the memory use of our program, we could go pretty far. There's quite a few tools in Python, especially in Python 3, for doing memory management. There's a tracemalloc module, and in the tracemalloc module, you can take snapshots. And when you take snapshots, you can see what got allocated in between those 2 snapshots. And so for a very simple example like this, we could see, is this thing really as large as I thought it was? And if you actually run this, you can see, on average, this line 11, which is the creation of this one object, had 48 bytes of additional memory allocated, so it probably takes about 48 bytes to store this structure, which is still very large, but at least we have some fixed bound on how big it is, and we can play around with trying to make it smaller. Now, bear in mind, another thing I would never advise you to do is, the moment anybody gives you a project that's, our application's using too much memory, can you figure out how to reduce that amount of memory? and by the way it's written in Python, just find a new job, because those projects are always giant dead ends, because even though this analysis kind of looks like it works, it only works like this because we're dealing with very simple heap allocated Python objects. The moment you start to do memory analysis on large Python programs, you'll see that there are structures within a Python interpreter, like free lists in your attribute lookup mechanism, that never get deallocated. So an actual Python program may not necessarily deallocate memory that it no longer uses. It'll just hit a high watermark and stay at that watermark. So all of these exercises where somebody says, oh, our app is using a gigabyte of memory, and how do you improve the memory usage? And then you go and you try and change a bunch of things, you won't be able to get the effects that you think you might be able to get. And fundamentally, unless you really understand what memory means, on all of the platforms where your application runs, like on your Windows platform, you understand what that VSS and that RSS and all that means. Or when you do free at your Linux terminal, you understand what all those numbers mean. It's a dead end. And so we won't go any deeper into this example, because this is pretty much a dead end career-wise if you ever get a project like that, and also analytically. Because the typical answer to this in Python is to use a mechanism provided by the Python object model called slots, which no longer, or in which a Python object no longer has an instance dictionary. So you save all that memory from that extra dictionary, and instead you have explicit locations for where the instance state of that type is stored. And so here, this particular object cannot store additional information outside of the number, manufacturer, resistance. If I try to amend this to add another field at runtime, it'll fail. You can see it'll fail. It doesn't have that attribute. And so it loses that dynamic behavior in exchange for, presumably, being a little bit smaller. In fact, in this case, it's not smaller. It's actually bigger. And so you can see, just don't bother with memory analysis in Python. It's not worth your time. Now, what you should do instead, and the guidance that I should give you, and it's a very important, very high-level piece of guidance for whenever you're writing a program, or even working on the example that we're going to look at after we go through some of these topics, is to think about Python as an orchestration language. Python was originally called, back in the day when we were trying to popularize Python, the ultimate glue language, the ultimate orchestration language, a language which takes components that are written in other languages, like C or C++, and orchestrates their mechanisms. And inside those components, which might be some kind of analytical code that somebody wrote 10 years ago that nobody wants to rewrite, but we don't want to today be designing experiments or setting up models and still using malloc and free, we want to have a nicer interface for that, well, then we reserve the manipulation of the problem, the manipulation of the business entities, or the manipulation of the experiment to the Python level, and the actual core computational use to this library in C or C++ or Fortran or whatever it might be. And so those entities turn into what I like to call restricted computation domains. A very common one that you're almost certainly familiar with is the NumPy ND array. If you think about it, a Python object is always boxed. There's no distinction in Python between boxed and unboxed objects like there is in Java. In Python, everything is boxed. And so everything is an object that you can call methods on that also is heap allocated and takes, or with the exception of certain things that might be interned or other optimizations, but for the most part are heap allocated and take a large amount of space. Whereas with the NumPy ND array, the contents of the NumPy ND array are contiguous machine types, so they're unboxed. Well, what happens in Python is you often design your system so that you have business entities that are unboxed entities. Then you put them into a computation domain like a NumPy ND array or a pandas data frame. Inside that computation domain, they get unboxed so that the computation domain, which restricts your access to those entities, can then perform certain specializations and optimizations. For example, putting these in some kind of cache contiguous structure so that you can do fast sums, or taking Python integers and turning them into machine integers with specific bit widths. So then you can use processor level instructions in order to compute operations on them. And you can see more or less that pattern occurs in any code example that uses pandas or NumPy or NetworkX or any of these other tools. And so in the case of NumPy, you might see some code that looks like this. You have 3 unboxed Python integers. You put them into a NumPy ND array. You perform some computation inside that array. Once it's inside that ND array, because it is a restricted computation domain, because NumPy says these are machine types, they are fixed bit width integers, so they are int64s. There's no interdependencies between these items. It can then choose to perform this element-wise multiplication in whatever fashion it finds is most efficient. So it can auto-parallelize it, or it could use machine-level instructions, or it could use some kind of more sophisticated processor-level instructions to vectorize this multiplication. And then you pull them back out. And so you can see there's almost always this case of you have the boxed object, you put it into the computation domain, which draws a box around everything. The objects themselves become unboxed, and then you pull them back out as boxed objects. And so this tends to be the pattern for where large object systems work. And so as we go through the example, one of the things you should think about is anytime you're working on some production system in Python and you're modeling in terms of Python objects, one of the limitations that you have is it's just going to be slow. It's going to be slow, and it's going to use a lot of memory. And it's going to be slow and use a lot of memory because Python objects are heap allocated and they're not contiguous. And so even if you have computations that should be local in some fashion, you won't get that locality in terms of where the objects are in the heap. And also, they're just huge, right? I mean, in the previous example, we needed 48 bytes to store, what, 2 strings and an int? That's a lot of space to store not a lot of data. And the reason is there's a lot of overhead for a Python object. You need to manage what the type is. You need to manage its reference count, and so forth and so on. And so what you should think is whenever you're designing a system like that, it'll inevitably turn into a situation where you draw some box around the business entity, some manager box, and inside of that you create a computation domain and then you restrict access to it. And that's how you get your performance back. And so one of the things when I talk about this, people sometimes bring up is they like to say, well, is a restricted computation domain a monad? And it's not really a monad. When you think about monads, you often think about putting a box around items and interacting with them only through some specific API in relation to that box. But what makes a monad interesting, I think, is the bind operation. And there's really no notion of a bind operation here. And also the ability to then provide combinators on top of them. We don't have that. This is a lot simpler than a monad. It's just some computation domain that gives you the ability to specify how the underlying data is stored and how you process the underlying data. So what happens when you do these things in Python is you end up having some kind of manager class, and you end up writing code that looks like it has some manager class that manages everything. And so for our resistor network, let's say we had some product that had some resistors on it. We ought to provide some computation on that. Maybe that computation would be that we wanted to sum or find the mean resistance of all these resistors. And so we might have some individual Python object that represents this boxed individual business entity that stores information that's not computational in nature. Like the manufacturer and the part number are not computational in nature. They're not used in any computations, but they're used for your production management of that system. For example, you ingest a bill of materials, and that bill of materials needs to know what's the part number and what's the manufacturer and what's the resistance. You then perform some computation, validate this product or this piece of hardware, and then you say, OK, I validated it. Now who do I go and send shipping orders to? And so you need that business information, but it's not actually used as part of the core computation. Then you might have some computational entity, and that this product here represents this computational entity. It takes the components that you give it, in this case just a bunch of resistors, and it extracts the information for them and puts them into a pandas data frame. Now if you remember how a pandas data frame works internally, it has this block manager. In the case of the pandas data frame here, it'll probably be a NumPy and D array. So effectively my manager class then has NumPy and D arrays, which are now contiguous machine typed structures where these computations be done very efficiently. And when I add a get item to pull items out of this computation domain, I can then restore the boxed Python structure by just reconstructing the resistor object on the way out. And so what you can see here in this example is, we start with a product and we give it a couple of Python objects. It deconstructs those Python objects to pull the information out, stores it in an efficient format in that pandas data frame. I can then perform operations on it, like I can do a .mean operation that'll then be performed in a very efficient fashion. And then I can ask it to give me the object back out, and it'll reconstruct the object on the way out. So this is how these structures tend to look. And you really wouldn't do something like this in C++. In C++, you'd often just write a C++ object, and you'd assume that the zero-cost abstraction nature of C++ would make this automatically efficient. In Python, you have to add this additional abstraction, this additional layer, because the pure Python objects are very good for orchestrating the operation you're trying to perform, but they're not very good at performing or representing the data in a fashion that is optimal for computation. So with that set aside, let's go back to our friend, the tuple. And we probably don't want to really use a tuple to represent any sort of data in our program. And even if we're doing simple data analysis, and the only sophisticated type we deal with is maybe our input data, and then we stick it into a NumPy and D array, we probably don't want to really use tuples past maybe the first prototyping stage. Instead, we might want to use something like from the collections module, the name tuple, which is just a mechanism by which we can automatically generate code that subclasses from a tuple object. And in that automatic generated code, it gives you very nice things like a nice printable representation. If we look at this code, you can see it gives us a very nice printable representation of the underlying object. And we have this dotted attribute access to these fields, so we don't have this unfortunate ergonomics of the tuple where we have to access the fields by position, and then if we add extra fields, then we have to go and update our existing code. Now, the limitation of the named tuple is that it's still a tuple, and so you still have that immutability, which may or may not be desirable for you, but fundamentally this is probably better than your underlying tuple structure. But if you were to show me some code and you said, I'm modeling some system and it's a production system, and I started by representing all of my objects as just built-in Python types, tuples and dints. Did I do the right thing or not? The real answer to learn from all of this is that one of the design principles of Python is spend more time with your family. In other words, if you're given a task, and that task is loosely defined, as most business tasks in a production context are, and you're told, I need you to do this one specific task, well then do the bare minimum that you can do in order to achieve that one requirement. And what you'll see as we go through some of these examples is Python gives you certain ways to take a very simple representation of an object and to increase its complexity as the complexity of the requirements increase. And so the answer is not in Python to take a C++ approach to designing an object, to designing your system. In C++, maybe the approach that you might take is you first think really hard about the underlying types that you're representing and the operations between them, and you write everything out. And if you get it right, then each marginal requirement that you get is only a very small marginal amount of work. And so you can think there's a lot of upfront effort, then a very small marginal amount of work as you go. In Python, we try to get something a little bit more linear in the sense that you produce a very marginal amount of work today, wait until a requirement comes in, and then see if you can extend that without causing changes to code that uses the code that you've written. And so things like the elevation from bare tuple to a named tuple in this example, because if I had started this example with just a regular tuple, other than the dotted lookup, anywhere else that this code might be used would work. And so turning this into a named tuple, turning this here into a named tuple just means that I add some functionality, but I don't subtract any existing functionality. I don't have to rewrite any code that was already using this structure. And so this is maybe the idea behind some of how Python is designed. Really keep it as simple as possible from day one. If you're given a requirement, try and get it done by 5 p.m. Go home, spend time with your family, and then wait until tomorrow when you get a new requirement to then escalate the complexity of the code that you've written. And so as we go deeper into this tutorial, we're going to see some examples where the complexity is indeed very, very, very high. And there's some mechanisms that are very sophisticated and maybe not mechanisms you want to use from day one. There are mechanisms that you should employ when a requirement says the only way for you to get this done with the system that you have written here is to use this sophisticated tool. Don't use it from day one because you're just going to be sitting writing code all night, and your family's going to be at home just crying. Whereas you said he'd be home at 8 p.m. So one thing that I want to draw your attention to, and maybe one of the motivations for why we're going to look into some of the sophistication, is if you look at where we started this first section of our tutorial with representing this resistor object as just a tuple, and you look at where we've ended up, representing as a named tuple, there's one little piece that's missing. In the tuple representation, we had one extra field, and that extra field was the type of component that we had. And the reason we might have that extra field is we might have some code somewhere that says, look at the type, and if it's a resistor, do this particular operation, and if it's a capacitor, do this other operation. Or if it's a resistor, then we know a certain relationship between the current that passes through it and the voltage. Or if it's a capacitor, it's a completely different relationship. It may be nonlinear for certain circuit elements. And when we turn this into a named tuple, we see that the code slightly changes. Instead of directly checking the type, we use this isInstance method that's provided to you in Python in the built-ins. And ultimately, these two blocks of code do the same thing. They're checking some object and see what its type is, and then they're dispatching on that type to perform some operation. This isn't even type-based polymorphism. This is just very simple check. Are you a resistor? Then do this. If you're a capacitor, then do that. Now, one thing that is very interesting and meaningful here is notice that the code at the top and the bottom is now moving towards using what you might call a shared vocabulary. One of the things that we can think about for the Python object model is that it provides us with a shared vocabulary that forces our code to maybe integrate better into the Python vernacular, into Python systems as a whole. In other words, if I ask you, give me an API for figuring out if a thing is a type of a thing. Well, one way that you could do is you could represent those things as tuples, and you could say, well, there's a field, and check to see if that field is exactly this string. Another way you could do it is you could say in Python, I'm given a built-in function, and it's called isInstance. And that built-in function reads to somebody reading through that code as asking this question as, is X a thing of this type? And how I implement that check may be customizable. And in this particular case, it is very customizable. And we'll see later how to customize that instance check. But fundamentally, what you're looking to do is you're looking to add a particular vocabulary, to employ a particular vocabulary that is available to you and made available to you by the built-in functions and by the objects, the data model in Python, so that your code reads very closely to the intention of what you have. And so when you read through this code, it reads as less mechanical, or it should read as less mechanical. It should read as asking the exact intention of what you were trying to ask. Are you an instance of this thing? Whereas this code here looks a lot more mechanical. Oh, is your 0th field this particular field? And it doesn't have that close correspondence between the intention and the mechanism that's used to express that intention. So let's talk about the basic object model in Python. What we know about the basic object model in Python is that we often use it to implement what we might call protocols. And so you can think for a very simple Python object like this resistor class, there's some protocol that represents initialization. And there's some syntax associated with that. And there's some close correspondence between the syntax that invokes the protocol and the way that we go and we implement that protocol. So for example, the syntax here would be this type name parentheses syntax. That is what we call initializing. And so when we look at this line, we say, OK, initialize a resistor with this particular data. And we need to implement what that means for this resistor type, so we write an init function. And the init function is very simple. It just sets fields. There's nothing more complicated than that. And if we do this, we can see it works and it's OK, although the printed representation of this thing doesn't look very nice at all. It's kind of ugly. And so we might think, OK, what's missing here? What do we need to implement in order to improve this printed representation? And we may know that in Python, there's a method called repr. It's another method provided to you at the built-ins, and it means give me the human printable representation of this object. And so what we might think is, given that close correspondence between some built-in function or some syntax or some TP or some rather bytecode, which we'll see in a moment, there should be some way to implement that protocol. And in the case of implementing the built-in repr function, it means implementing the underscore repr data model method. And so if we go ahead and implement this data model method, then we've satisfied the ability for this object to get a human printable representation. And you can see here, when I print this out, it has a human understandable representation. It doesn't tell us just the type of the object and the object's ID. It tells us information about that object. Now, if we go to the part of the Python documentation, docs.python.org/3/ I don't know, just go there and then find it from there. You'll see that, actually, just Google for data model method or for data model Python. You'll see that there are certain rules around the implementation of all these protocols. There are certain guidelines. What you'll see often is that these protocols are rightfully called protocols because usually what you're doing is you're taking some fixed mechanism by which you answer a question or perform some operation. You're hooking into it to add some small amendment or some small addendum or some small modification, and then you're dispatching back to that same protocol on either a constituent object or on a base class. And so one example of that is if you go to that data model page and you look at the rules around repr, one of the rules that people generally try to abide by when they're writing their repr is that the thing that this prints out, you should be able to cut and paste in your Python terminal. And when you cut and paste it, you should be able to create an equivalent object of the same term. But that doesn't work because you can see this is a numeric expression, not a string. And this is a variable name, not a string. So there's something missing here. I need to put extra quotes around that. It may seem like a very minor thing. Oh, I'm just missing some quotes. I should just add some extra quotes here. And if I add these extra quotes here and here, then what I get is a repr that conforms to the standard practice, where if I cut and paste this line right here, and I paste it on my terminal, I'll get another resistor object that should be equivalent to the first one. But what you might think is, well, this case it may not make sense, or maybe it might make sense. What if this field here has double quotes in it? Maybe that field has single quotes in it, and then I have to figure out how to do that quoting, and I have to come up with some complex code to figure out how to quote that thing or to escape quotes in that thing. And instead, what I'm missing is that final piece, which is these protocols almost always dispatch back to the same protocol on either a constituent object or on a base class. And so the answer here should be something like this. The only real change that I've made is I put a bang R at the end of this I put this field formatting specifier in this f string. And what that means is, this is the equivalent to just calling repr inside my repr. These are equivalent. And so the guidance here is that whenever you're implementing one of these protocols, almost always, you're going to call the protocol from within the protocol. And so all you're really doing in that implementation of that protocol is just adding your slight modification and then dispatching back to the protocol to do the work as expected. And when I finally make this work, and I add an EQ here so that I can actually see they're equal, and I cut and paste that result that'll be printed out in this line over here, we'll see everything works as expected. And so I get the resistor printed out nicely. If I cut and paste it at my terminal, it's back equal to the original object. And so that's the general guidance that I have for repr. This is why you might, this may answer why, for example, if you've ever opened a file in Python, say the file that we'll look at in a moment, network.json as f, and you tried to print out the repr for that thing, and you looked at it, you saw it had angle brackets before and after, and some objects you might see in Python have those angle brackets before and after. You might wonder why that's in the repr. Well, this is not valid Python syntax. And so in some cases, it's impossible for that human printable representation to give you something that you could cut and paste and get an equivalent version of the original object. In the case of a file, it's because there's going to be a lot of hidden information here, like the file pointer at the operating system level, or certain buffers that may not be recreatable in any fashion, or there could be write buffers that you may not be able to recreate in any fashion to reconstitute this. And so they explicitly put these angle brackets before and after the repr to indicate that what I'm showing you is a human printable representation that could not ever be reconstituted into the original object because there's some hidden state that is impossible for us to capture. It's no longer some kind of immutable or stateless object like our resistor type was, or some object with some controllable and visible and manageable state. Now, it turns out that this stuff can kind of be a little tricky to get right, because let's say I start with my resistor and I add in like a variable resistor, like a potentiometer, into this problem. And my potentiometer just subclasses from my resistor. Nothing too fancy. And I create a potentiometer here, and maybe I should call it P for potentiometer. And then I just try and print it out. Nothing fancy at all. What you'll see is that the repr is wrong, right? It tells me it's a resistor, but it's not. It's a potentiometer. And it's simply wrong. And the reason for that is, when I wrote this repr originally, I hard-coded the name of the type. And so maybe I need to do something fancier. I need to dynamically present the name of the type as part of the repr by actually looking up the type at runtime and printing that out. Now, is this an actual improvement? Well, in this particular case, you can see it prints this out correctly, but this isn't quite an improvement. Because it turns out that this idea of dispatching back to the underlying protocol doesn't always work for every protocol in a very nice fashion. It's often the case that you do have to just go and write the boilerplate to re-implement something. And repr is a very clear example of that. Because if in my potentiometer class, I then add in maybe the max and the min and the max resistance. If you remember, a potentiometer has kind of a slider on it, and you kind of slide it there, and it goes between two levels of resistance, and then wherever the slider is, that's the current resistance. So maybe I add in a min and a max resistant field, but then the rest of the fields are the same as the underlying resistor. So it really is just extending this underlying resistor class. I got to write a new repr because I have these extra fields I need to print out. And how does this repr up here know about those extra fields? It might be able to dynamically figure out what the type of the class is, like we saw in the previous example, but it'll never be able to figure out to print out those extra fields as well. And so I'll have to rewrite this. And actually, I missed one field here, so we'll add in that extra field. So I should do it like this. So there you go. Now, you might then look at this and say, something doesn't sit right with me. Because every time I implement these protocols, like I implement len or getAttr or getItem or call, I'm almost always invariably reinvoking that protocol. And here I'm not really doing that. There just seems to be a lot of boilerplate with this repr. And unfortunately, it's unavoidable, because the only other way you can avoid this is if you go ahead and try and create your own protocols or your own object system. And so here's an example of something that you might try to do. You might try to tell the resistor type here, you know what, these are the fields that you have. These are the fields that you have. And along the way, we'll also make those slots, because for some reason, people seem to really love talking about slots, even though I think they're just absolutely boring, as can be. And so because I can identify what the fields are, then when I write the repr for my resistor down here, I can just have it dynamically pick out what those fields are going to be and print that out. And then that means that any subclass of this just needs to say, oh, I'm a potentiometer. I'm just all the resistor fields plus these 2 extra fields, and I get that repr for free. And what you can think that you're doing here is you're kind of creating your own universe, your own set of protocols, your own object model. You're creating a set of guidance or set of rules that every type in this hierarchy needs to abide by in order to be consistent. Because it could be the case that, for example, you subclass something from this, a different type of resistor, and this is some other type of resistor, and you forget to fill in the fields. And if you forget to fill in the fields, then the repr doesn't work and everything fails. And so you might additionally need to add in some guarantee mechanisms or some mechanism by which you can enforce from the base class down to the derived class that you fill out this object model. But fundamentally, what you're seeing is you're beginning to diverge from what a normal Python object, what the rules of a normal Python object dictate by adding your own rules. If you create your own subclass here, you also have to fill out this extra field structure. Otherwise, you start to potentially lead to inconsistencies in the way this operates. But for the most part, this works. Now, is this worthwhile? Is all of this additional mechanism worthwhile? In this particular case, no. All you've saved yourself is a little bit of boilerplate that you would have written just written once. That would have just been a cut and paste job. It's almost certainly not worthwhile to start adding these complex object systems on top of the Python-based objects just to save yourself a job that you just give to the intern, right? And so there are definitely cases where you want to build up these object systems. For example, if you're designing a library, like an ORM, of course you need to have some kind of object system, and you need to have a tight set of rules for how people subclass from your base ORM object. But at something as simple as this, no, it's really not worth it. And so I think one of the other guidances for how to make best use of the Python object model is really don't overthink it. Sometimes there is just cut and paste. Sometimes there's boilerplate. Whenever you're writing your inits, there's some necessary amount of boilerplate there, and just live with it. Just learn to live with it. Because trying to get around it starts getting you into this deeper and deeper and deeper hole. Because, for example, this object system has other duplication, right? These fields here are repeated here. So am I going to automatically generate the inits as well? And what if the init needs to take some modality that's not part of the field? And then how do I build into that abstraction the ability to have these additional modalities? And this is just going to become more and more and more complex as it starts to interact with the real world, whereas the cut and paste approach would give you that infinite flexibility where, oh, this particular subclass needs to have an extra flag, and that flag is not a field, it's just some modality flag for guiding the rest, like the units in which the resistance are in. And then you can see that just everything will fall apart. And so you really have to be judicious about using that. Now, if you really wanted to be clever, you could really try very hard to use some of Python's introspective nature in order to get around not building your own object system. But fundamentally, you're basically doing the same thing. And so in this example here, instead of identifying what the fields are, I use the inspect module signature to look at the signature of the init, to figure out from the signature of the init what the fields would be, and then to automatically generate the repr from that. And so the magic line here is just this line here, which figures out what the fields are, and then automatically prints them. So you can see both of these reprs work. This repr here works even though it hasn't been implemented, and I haven't specified what the fields are. But again, I have this fundamental problem where if there were some modality here, this modality would be interpreted as a field, not a mode, and I'd have to say here, oh, look at all of the parameters to this init function that happen to not be keyword or only arguments or whatnot, or you'd have to get people to say, this is a read-only field. They'd have to use annotations or some nonsense like that. And you're just adding a lot of complexity for what is really just a little bit of boilerplate that you just have to suck up and write. Now, all of this kind of discussion of an object system or creating your own object system should remind you of something else that you've seen in the Python standard library. Python 3.7, we got in the standard library our own version of tools that have existed outside the standard library for some time, which is automatic generation of the boilerplate for a class. In the standard library, they're called data classes, and these are mutable types that automatically generate a repr and an init for you. You use the variable annotations that were added in Python 3.7, I believe, in order to specify information that's never actually used anywhere. So don't think that this is actually checking that these are strings in a float. No, it doesn't actually do that. But maybe your type hinting tool does that. I don't know. I don't use those. I don't think they're that useful either. But you get a lot of code for free. And so from our perspective of doing the least amount of work in order to implement the system I think there's something worthwhile here. And I am personally a big fan of data class, although I would say, it doesn't really matter what you put there, unless you're really using the type hinting stuff. Although, maybe, if you were to extend data classes yourself to add your own mechanisms, you might put something here that might be more interesting, like some automatic validator or initializer, something better than the PEP 484 type hinting stuff. Because, the variable annotation just gives you some structured place to put some information, which you could then retrieve as part of your object system. Now, one of the things I want to draw your attention to is that, as we can see, and as we saw in the previous example, as we get deeper into the Python object model and we implement all these underscore functions, we're effectively creating a vocabulary that describes how our objects interact and how we interact with those objects. And so in this case, we have some network of circuit elements, and we can ask that network, how big are you? Like, how many elements do you have? What would that mean? How many elements you have, how many connections you have, how many nodes you have. But there is some particular meaning that you might assume when somebody asks, how big is this network? And the way that you might implement that is by using len. Len is a very natural way in Python to express, I'm trying to figure out how big this thing is, and then you implement it with your underscore len. Or you might need to retrieve something from this network. For example, you might need to retrieve one of the elements by its part number. And you can think this idea of retrieving something corresponds in Python to the square bracket syntax, and so you'd implement get item. And this would be better than writing your own get part by number function or your own get size function, because what you're thinking is that the thinking behind this is by sticking close to the vocabulary provided to you by the built-in functions and the Python-based data model, what you're doing is you're reusing a vocabulary that already exists that describes the way that Python objects that people are very familiar with interact. You're encouraging the objects that you create to better integrate with the core language itself. You're encouraging the code that you write to minimize the additional entities that somebody needs to understand in order to understand the code that you wrote. And so I would say that implementing len might be a net benefit over writing a get size, even though you might say this is more explicit. This is something where a Python programmer looks at len on an object, and they intuitively think, this is saying what's the size of this thing. And as long as this network has one unique privileged notion of its size, in this case, we're assuming that that would be the number of elements, then this produces code that's fluent, that integrates nicely into existing Python code, and that minimizes the amount of additional API documentation we have to have. Because you can think here, if you had a get size, you'd have to write some API documentation, and I suspect that the API documentation you'd write for len would be much smaller. Len would just be give the size of the network in elements, whereas here you might need to add additional qualifications. Now, unfortunately, one of the downsides is it's not always clear where this or how this vocabulary is specified or what the terms in this vocabulary mean unless you've been using Python for a very long time. And there may be cases where you look at how Python works and you might assume that there's a vocabulary in place when there really isn't. And one example that I ran into a very long time ago was the hash method in Python. We know there's a built-in function called hash in Python, and if we look at that, we could say, oh, this gives us some unique identifier for an object that might represent this object in a fixed space, in a fixed integer space. And so I might then use that if I need to store my objects in my own custom object database or store them in some fashion that needs to be retrieved off of disk. I might say, well, I need to find some way to compute this hash. You know what? I'll just use the built-in hash protocol. I'll use the built-in hash function and the underscore hash method, and that's how I'll make it work. But unfortunately, that's not what hash means in Python. Hash means something much narrower in Python. It means give me a single integer that can then be used to compute what the array index for how this thing will be stored in a set or a dictionary. Because, for example, if you have a Python object and its hash always returns -1, it does not always return -1. It is impossible in CPython for the hash of an object to be -1. It always gets coerced to a -2. Why? Because deep in the bowels of CPython, this -1 value is used as a C value to indicate that there was an error in the computation of the hash. So every time an underscore hash method returns -1, it gets coerced to a -2. There's a line of code there where it says if it's -1, return -2. And so you can think, why does this make sense? Because this doesn't happen in PyPy, it doesn't happen in any alternative Python, in any non-CPython implementation. Well, it's because this protocol does not mean, oh, just compute a hash that could be used in many different places and could be used in order to store this in an object database or store it on disk. This means very specifically and very narrowly, compute something that will be used by the Python interpreter itself for the purposes of that running instance of that Python interpreter and no more. And sometimes that small and very subtle distinction may not be visible when you're reading through the documentation or reading through Python code. For the most part, these corner cases are fairly rare, but there are these corner cases where you look at something and you say, oh, this is a nice way to express an idea using the Python data model, and it's not because there's some nuance there. For example, if you look a little bit deeper, hash may also, in some cases, add some randomization factor in order to avoid DDoS attempts for Python systems that are built that have some kind of user exposure. And so what the actual hash value that's produced by this method may not always be predictable, and it may change between different invocations of the same interpreter with the same version of Python and the same code base on the same machine. And so it's not something that you can reliably use to compute something. And so in this case, it would actually be the case that if you wanted to have your objects serializable into your own object dictionary, and they need to have some unique identifier in that object store, then you might actually have to write your own hash without the underscores function, and you might have to now duplicate the entities, because this object here might then have both a hash of something. I'll just do. It may have both this and its own hash method. And this may seem unnecessarily redundant, but this one is being used for internal use by the Python interpreter, and this one's being used for some kind of external protocol. And so being able to distinguish what these protocols are, whether they're actually for broad use to describe the interaction between your object, or they're just used for hooking into the Python runtime, can sometimes be a little bit tricky to see. Although I can tell you that there's fairly few circumstances where this occurs. Most of the time, you can reuse these protocols to express whatever meaning you want. An example of that would be, and this may make some of you think of the pathlib module in Python. And one of the things that people like about the pathlib module is that it gives you controllable programmatic access to paths. Like you can switch out suffixes, you can get parent paths, you can resolve them, you can get relative paths and absolute paths, instead of having to do string manipulation. So what you do is you put that string into some structured, you put that string data into some structured object. That object then gives you structured ways to manipulate it. But other people like it because you can use the solidus, you can use the slash to mean the same thing as like, directory slash directory. And this I think was controversial because I think a lot of people really objected to the use of what appears to be a mathematical operator to just kind of do some cute syntax. And you can really go as far as you want with this. And so here's a stupid example of using matmul, the @ sign, to automatically generate emails. This is absolutely pointless. This is not an arithmetic operation. All of the assumptions that you might bring to matmul, like for example, it performs some non-element-wise operation. It may not be associative, or it may not be commutative. Those all break. This is just gimmicky syntax. And some people seem to like that. I don't know. I think you can go a little bit too far. So this is an example of going way too far. Now that said, pathlib, for whatever reason, people seem to like. So you can't complain too much. Now, let me dive a little bit deeper into maybe some of the motivation behind all of this, because I think that sometimes looking at some of these mechanics might be overwhelming. And so I want to give you a case study, a real-world or simplified example of a real-world case study of where some of these mechanisms are valuable. And one of the thought processes you can have for when you might use some of the mechanisms, especially some of the more sophisticated mechanisms we're about to look at, is to think about how use of the Python object model not only can give you this common vocabulary to describe interrelations between your objects, but it can also give you the ability to rearrange the complexity of your program to serve certain human needs. So I'll give you an example. Let's say that we have a simple report, and that report has some information before and after. So we've actually done the circuit analysis, and we figured out where the currents are, and we can see, given some layout of the circuit, some dialing on that potentiometer, the currents are where they were in the before line, and then after we dial that potentiometer differently, the currents are there. And for some reason, in this particular example, one of the currents dropped out and the other one dropped in, so maybe we dialed one of the potentiometers so that there was no longer like a span between those two nodes. And one of the things we might want to do is we might want to actually compare, like, what's the before and the after. So we might want to generate a simple report. I'm going to generate a simple report that looks like this. These are the before currents, these are the after currents, this is the absolute delta, and that's the percentage delta. And it turns out that in many fields, This report was actually something that I spent quite a bit of time doing when I was building P&L systems for front office trading desks, because it was often the case that what you'd have to do is you'd have to come out with a new financial model for a bond, and you'd have to see how that model compared against the old model. And so you might price this over a set of days and look at the differences. And one of the common things that when you generate a report like this, somebody asks for is they want to be able to flag things that are severely out of variance. Because if you look at the differences here, you can see for current 1, it went from 10, I guess, amps to 14 amps. That's a meaningful change. Current 2 went from 15 to 14. That could have been, if we were using some kind of Kirchhoff's, Laplace, inverse matrix formulation, this could have been some kind of rounding error, so that might not even be worthwhile to look at. And then here you can see this current 5 went from 1 to 50, so clearly something went really wild with resistance on that span, because we increased the current by 5,000%. And so how might we want to look at that? Well, in the confines of a very simple text report, maybe we'll just add a little star to the end of the lines. We'll, at the end of the lines, add a little star. We'll add a little flag. So we'll say, looking at the percent difference, if it's greater than 50%, add a star star. If it's greater than 10%, add a little star. And as simple as can be, if we look at our report now, we can see, oh, we starred that and that as being very meaningful things to look at. It's a very common thing to do. Imagine if you're comparing 2 runs of a model, and you need to figure out where were the meaningful changes from day 1 to day 2, or where were the meaningful changes before and after we made a change. Now, the question is it likely that this functionality here, where you're constructing that flag, is it likely that might appear in different places within your system? Of course, because the guidance for how you generate this flag might be something that is necessary not only in this particular report, but in any other subsequent report that you do. Maybe you have some model and you're looking at its performance, its memory use, or maybe even you're looking at its predictive capabilities, and this flagging, this percentage flagging, is something you want to use in all 3 places. And so instead of cutting and pasting these 5 lines of code, you need to find some abstraction that allows you to reuse the same flagging mechanism, the same percent flagging mechanism in 3 places. Now, as a data scientist who's maybe mostly familiar with writing functions or mostly comfortable with writing functions, you might say this is a perfect example of refactoring. Just extract this to a function. So I have a simple function called getFlag. I give it the percentage difference. It looks at the percentage difference, and it gives me that flag. And I generate my report from that. And everything works as I expected. And now in the different parts of my system where I need to use that flag, I just reuse this function. This is very basic modularity, right? But I want to suggest to you maybe a different approach to take. And a different approach to take that might comport a little bit better with what we've been looking at so far about building this common vocabulary, but also about how we can rearrange the complexity of a program using this Python object system. And so as an aside, I have a small question for you. We know that there exist many protocols in Python, like getAttr, getItem, and call. GetAttr is for looking up an attribute by dotted name syntax. GetItem is by looking at something with square brackets. And call is whenever you invoke something with the parentheses after it. What is the difference between these 3? Clearly, there's a difference between getAttr and the other 2. Because the argument for getAttr is always a string with maybe underscores in it, but you can never really implement getItem with getAttr. That's impossible. But what's the difference between getItem and call? Like, why does it matter if I chose in my protocol to use square brackets here or parentheses? You might say what it conveys to the reader of this code may be different. In this case, you're conveying look something up. In this case, you're conveying compute something. But mechanically, there really is no difference. The code here is the same. The protocol is different. The syntax is different. But it may not be clear where that difference is. Now, putting that aside, let's rearrange the complexity in this original example. Instead of having a function that gets the flag, let's create a structure. And we'll call it a range dictionary. And just like a normal dictionary, it'll look things up. But unlike a normal dictionary, it won't look things up exactly. It'll look things up belonging to some range. So if the value that it's looking up is between the range of 0 and 10%, it'll give me just an empty string. 10% to 50%, it'll give me a single star. 50% to infinity, it'll give me a double star. And then I'll amend my report. So in my report, I just look up the flag using this lookup. And that kind of makes sense, because we know that square bracket kind of means look something up. So this means, in this very last line of my report, look up the flag given the percent difference. And we can see there's a very close correspondence between what we originally wrote, which used a function formulation, and we're writing here, which is using some kind of lookup, some getItem formulation. Now, the actual mechanism that we might employ to make this work might look something like this. We'll have range dict subclass from a dict. It'll implement part of the dictionary protocol called missing. When you look for a key that doesn't exist, you invoke this. This is a very inefficient implementation because it's a linear search through the ranges. But you can imagine that you could recode this as a more efficient, maybe logarithmic search through the ranges. And you could also even add some logic up here that makes sure that the ranges are not overlapping and that there's no gaps between them. But fundamentally, beyond all of those mechanics, and I'll hide this mechanics here, I want you to think about how this is different than the first example. Here, if we compare these two, in the first example, we have a function called getFlag. We have one function called getFlag that tries to figure out what the flag should be. And in the latter example, we have a piece of data that indicates the flags and a type. And you can see there's the same fundamental complexity in both of them. In fact, the same operation exists in both of them. If we wanted to make the first one generic in the same way this is, we could pass in the ranges as a piece of code, as some input data, and we'd have some code that looks like this inside of that function to figure out, are you within the ranges or not? But fundamentally, what's the difference here? Well, I think what you can see is that what we've done is we've taken that fixed amount of complexity and we've moved it into two places. We've moved the complexity for the lookup mechanism into the type. We moved the complexity for the data that feeds that lookup mechanism into the data here. And so we've taken that complexity and we've splayed it apart. Now, is that beneficial or not? Well, this is a lot more sophisticated in terms of the use of Python than the first example. But what you could think is, if these ranges were to change later, it'd be a lot safer to change it here than to change it in the first one. If you wanted to make sure that this was done correctly, not programmatically, but just by eyeballing it, it's probably a lot easier to eyeball it here than the first version. And so you can see that when you can rearrange the complexity in your program in the right way, you might facilitate certain human actions like refactoring, maintenance, or the confidence of correctness, maybe not automatic or verified correctness, but just human understandability of the code in different ways. Now, all of that should remind you of something else from the Python standard library, our chain map. And our chain map is a perfect example of this. It's often the case that in the problems that we solve, we have some mechanism that we see somewhere that looks kind of like layers or scopes or something like that. There's some lookup, and there's some way to add some layer in front of that lookup to modify that lookup. And that's exactly what the chain map is. It's a data type that gives you this chained lookup. And so in the chain map, you might have two resistors, and this may be part of some simulation example you're trying to do. For example, you might have the resistance of the network supplied by the chain map, and then when you want to test something, you might push into this chain map a new value for the first resistor, and when you're done testing, you might just delete it off the front. And what you can see when you run this example is, the value of this resistor goes from 10 to 15 to 10, because the chain map is just a ordered lookup through these different maps, and the first map that it finds it in, it returns that value. Now, you might dislike this because you can say, some of this list manipulation using del and insert is probably not particularly efficient. We're always told to try and avoid those structures. If you want to, you can always be cute in Python. People might advise you not to be cute, but you should be who you are. And so you could always swap out the maps and the chain map for the deck. And now you have very high efficiency insertion or removal from either side of the chain map. And so now you can write a very high performance kind of almost sort of like a copy on write or a cheap view mechanism on this underlying data. Now, you probably might not want to use the chain map directly, but you can think if you lift that up into your own custom type, then you can have your custom type have this very nice automatic undo behavior without having to employ a very sophisticated mechanism, taking the sophistication of how that undo works and isolating it in the type itself and using something from the standard library to do that. There are some severe limitations to this approach to writing Python. One of the questions I asked you before was, what's the difference between getAttr, getItem, and call? And getAttr is very, very clearly different from the other two. GetItem and call may be very similar. Here's an example of three things. And I'm curious what the difference is between these three. A named function, getItem, and call. And I can do the same thing. It's just the syntax is very, very slightly different. I switch between parentheses to square brackets to a dotted name lookup and then parentheses. Just very slight differences here. What's the fundamental difference? Which one do I choose? I'm told that maybe I should choose one of these two because this adds unnecessary entities for somebody who's reading my code to try to understand. So they have to look up what this means, whereas here, there may be some certain assumptions that if you correctly abide by, somebody can read that code and not have to just take the assumptions that pop into their head and continue understanding what the code does at a very high level before they have to dig into the documentation. Whereas every time you have a dotted function, somebody's going to really feel like, despite what its name might be, I really need to look at the docs for that. And so maybe that's one guidance, but that's a human guidance. Is there any technical distinction between these three? And it turns out that there are. There are some significant ones. First, what if you need to pass 2 arguments in? You can't do that with getItem. GetItem takes literally 1 argument. It's just a thing to look up, right? Whereas call can take as many arguments as you want. Now you might say, well, that's not such a big deal, because if I pass in 2 arguments, I'll pass them in using the same syntax, but they'll be passed in as a tuple, and I'll just destructure that tuple there. That's a little hokey. But where this really breaks is, what if you need to use keyword arguments? There's no possible way to add keyword arguments in this structure unless you start mimicking like JavaScript, passing objects to functions. There's no other way to add keyword arguments here with the nice syntax, whereas with your call, there's a way to do keyword arguments. And so what I said originally was, oftentimes what you might do in Python is you might start with the simplest implementation and then increase the complexity as the complexity of the problem you're trying to solve increases. When you're choosing how to implement the parts of the data model, that may not always be the case, because sometimes you can code yourself into a corner. For example, imagine that this type here represented some kind of object database, some storage, and you wanted to use the square bracket lookup to pull some object out of that database by a path. But then you need to add a modality to that. Are you running against the production database or this database? Or are you doing a dry run versus a non-dry run? Or are you doing a verbose or non-verbose? You immediately are no longer able to use the square bracket syntax because it can no longer accommodate that keyword argument modality. And so you have to drop back into using maybe the call protocol, and you'll have to go and rewrite a lot of code. And so sometimes being very judicious about how you pick which protocol that you implement may be important, because switching between these is harder than you might expect in certain cases. Or there may be sufficient technical requirements that force you into one of these versus the other. Now you might say, well, as a precaution, I'll always only use call, and I'll never use square brackets, I'll never use getItem. But that may not be a wise or judicious move, because there may be cases where this getItem really is the most natural way to look at it. But you really have to keep at the forefront of your mind, what are the limitations that I'm buying into? There's another also very serious and severe limitation here that we haven't talked about at all, but we've hinted at slightly. And I want to talk about one thing that you may have seen and you may have wondered about, which is a class method. And oftentimes when people talk about the object model, they kind of think about the object model as, well, there's a bunch of underscore methods, there's properties, there's static methods, and there's class methods. And that's about it. And they might talk about class method as, oh, it doesn't take an instance, it takes a class, and static method doesn't take any arguments. And that may be as deep as they go. But instead, I want to guide you through a different way to think about some of these things. And one of the other serious limitations of how you choose to use a Python object model to implement this common vocabulary. Here I have a simple network that's initialized with a set of resistors, and it just stores that information. It doesn't do anything interesting with it, right? What if this data came from a file? Should I write my init like this? Maybe it takes a file name. And if you provide the file name, then you open up that file and you read the resistors from that. And it's a very common thing. I might not always want to instantiate this object from data that exists written out in my program. I want to give it a file and have it figure out how to read and parse that file and do something with it. And so you might say, oh, that's not so bad. It's a little bit clumsy because I'm not sure what I do if I provide both this argument and this argument, but it's not so bad. Don't do this. One of the guidances that is not explicated in the data model documentation for Python is guidance around what an init should look like. And as I told you previously, sometimes it's not worth creating your own object systems, your own kind of pseudo versions of data classes.data class in order to avoid writing boilerplate. And one of the two common boilerplates that you might want to avoid writing are repr and init. My guidance for you is this. Init is always and should always be boilerplate, and it's just boilerplate, and just leave it at boilerplate. Your init should almost never do anything fancier than setting attributes, checking that you're constructing a valid object, or constructing derived information. You'll see an example later where we construct some derived information, like we take the connections of a network and we infer maybe what the elements are. But here, doing something like reading from a file is a terrible idea. You know why? What format is this file in? Is it an XML file? OK, great. I have the data in CSV format. What do I do now? Am I going to pass it an argument called file name equals this, and I'm going to say if file name is not none, if, and I'll use pathlib, file name dot suffix equals Excel, do something here. Otherwise, if it's something else, do something here. No, this is going to be atrocious, right? And certainly, I do not want to do, maybe it doesn't come from just a file name. Maybe it comes from a file name or from a database. Do I want to pass extra arguments? And I have all these different ways to construct it, and all the number of modalities in my init explode. And fundamentally, if I construct it from a file name, the repr should probably indicate how it got constructed. And then you're going to find that round tripping of the repr to the init, it's going to be very difficult to make it consistent. Fundamentally, what you can also think is here, and this is one of the serious limitations that you have to keep in mind when you're designing objects in Python. The protocol methods give you a common vocabulary for how to describe the interrelations between your objects, assuming that for each element in that vocabulary, there is one privileged, unique meaning for that. So in the previous example, we talked about a network, and we talked about using len to figure out what the size of the network was. Is there only one meaning for the size of the network? Well, maybe, maybe not. Maybe in our use case, the only one meaning is the number of elements. But in another use case, if we were, for example, doing some kind of mesh analysis, maybe it's the number of meshes. Maybe we need to surface both use cases, both the number of meshes, number of loops that we're going to compute, so that's the number of rows in our Laplace matrix that we'll actually have to compute the voltage and the current on the matrix on, or of the network on, and maybe also the elements, because we have some production need to say, okay, this thing pass some verification step and go through these elements, and this is how many elements you're going to have to purchase in order to produce this network. If there are two meanings, which gets to use the underlying protocol method? You can see this problem here. Here, we're saying there's many ways to initialize this object. You can initialize it from the actual data, or from a file, or from a database, or from something else. Which one's the one true right way to do it? And if there is no one true right way, one unique privileged way to implement that piece of vocabulary, that protocol, then you should not use a protocol at all, because you're going to end up confusing somebody, because they're going to call len, and the result they're going to get is not going to comport with their assumption for what you meant by the size of the structure. Similarly here, this init, the arguments that you pass to it should comport with somebody's understanding for how to initialize this. Now, init is special in the case that an object must have an init, whereas an object doesn't necessarily have to have any of the other pieces of the protocol, of the data model. And so the guidance there should be to always have the unique singular meaning for your objects, for the initialization of your objects, to just be initialize them with the raw underlying data and do a bunch of boilerplate to set this object up, and don't do anything interesting, don't do any stateful actions, don't read a file, don't read from the database, don't do any of that. That should be the answer. And what you should instead do is use class methods. Think about what class method does. It gives you a class from which you can derive whatever you want. And so what you could think is all the different ways to construct this object that are not constructing it from the raw data itself can be a class method, because class methods are not singular and privileged. You can have as many class methods as you want. If you want to construct this from a file, you can use a class method called fromFile. If you want to construct it from an Excel file, you could use one called fromExcelFile, and these can be duplicated as you desire. And so a class method is not only this idea that you have some method that gives you a class, and you can from that construct an instance, but also the idea that this is a mechanism by which you can add to a class protocols that are not unique and privileged, but instead might be duplicated in order to satisfy a variety of use cases when there's not one privileged way to, for example, construct an object. And so that's the general guidance for where class methods tend to be used, what you might call factory functions. And the reason why they're used in that fashion, and you should never use it in init, is we no longer have one privileged way to construct this object, but instead we have multiple possible ways to construct it. Now, with that said, let's dive a little bit deeper into the object model. And I'll touch upon a couple of small things that you might be interested in or might be useful to you to know. Here we have our name tuple representation of the resistor. And nothing too fancy there. Now, when we look at this example here, we can see, oops, let's do this one first. We can see that there's a problem in the data we've passed. We passed a negative resistance, which for the purposes of our example shouldn't really exist. These resistances should always be positive. Now, it may be the case that in our program, that's not an error that anybody makes, and so maybe we don't need to do anything about it. Maybe this is something that could just as simply be caught by code review. But if it were the case that it was not something that could be simply caught by code review, or there might be some additional value to catching it ahead of time, then we may need some mechanism by which we try to catch that error. Now, one of the things we could try to do is we could try to take the name tuple, subclass from it, and implement new. And in this new, we could check to see if the resistance was negative, and if it was, then to provide an error message. And to say, oh, it's got to be a positive number. You gave me a negative resistance. And then that gives us some better guidance. But the thing is, if it's a name tuple, this thing is immutable. So that's a fair thing to do. But if we need this resistance to be mutable, for example, it's that potentiometer where we might dial it back and forth to change the resistance, and it has to just be between the min and the max value, then it very well may be the case that we need to change the resistance later. And here in this case, we can't change the resistance because this thing is a subclass of a tuple. It's immutable. But if this were a rich object and we needed to be able to change this, then we'd need to figure out some way to do that. Now, if you were Java programmers, circa Java like 2015 maybe, we might write getters and setters. We might say, in order to prevent this update anomaly, or in order to prevent this anomaly whereby we change this field to an invalid value, we're going to force you to go through this getter and this setter to interact with the underlying data on this class. And so here, this check that we put up here might also be duplicated down here. And we do fundamentally get the ability to check that if you set the resistance on this thing, if you mutate this thing and set the resistance, that it's this would be value, that it's indeed positive. Now, the problem here is that how do we choose when to write our getters and setters? In fact, we may decide that every field always needs to have a getter and setter because there could always be some need later down the line to add validation. How do we know ahead of time that this is the validation we need? And we're told as a guidance that we should never write code that hasn't been explicitly asked for us because it's just going to add more lines of code that we then have to refactor later as the business problem changes. And so there's something missing from here. Now, what you might already know, the answer is that this is why the property pattern exists in Python. This is why the property decorator exists. The property decorator gives you the ability to add in hooks into the lookup or setting of an attribute after the class has already been constructed and already been used. And so here in this example, I just use property. And then when you try and pull out the resistance, you pull out this field that has been demarcated as being private. In this instance, when you're trying to set it, we put the check here, and then the code works. Now, the guidance here is that not just that this is something that we didn't need to have from day one. In fact, our first version of this code might very well just look like this. Right? Could just very well look just like that. It doesn't do any checks whatsoever. And maybe there's a bug there. But maybe if that bug is not common enough, it doesn't warrant the effort for those extra 7 lines of code, and that's fine. And then when we discover that there was a requirement, we can add in these 2 checks here. It'll start to catch invalid code more aggressively. But the rest of the code that we wrote for this no longer changes. The API doesn't change. So we don't have to go from having a raw attribute to a setter and a getter. However, another thing that I would like you to think about from this is that what is the difference between a property and a named function? They both can compute something, right? Like there's both space here and here to compute something. So what's the difference between this and this? Well, clearly, you can't fit arguments into the property, right? So the property can operate on the state of the class, but there's no way to fit in either positional or keyword arguments. And so just like the difference between getItem and call, you can see there's a functional, there's a formal difference between these two. There's also another difference, which is typically when somebody looks at a property, they don't expect there to be a computation that's very time-consuming or that has stateful effect. Whereas with a call, there's usually a free assumption for something that might have stateful effect. Now, as we said before, why not just always use this syntax? Why not always use call? It's the least restricted. One of the other principles I think of Python is, you'll often find in Python that there are dualities. There are structures that are more flexible and structures that are less flexible or more constrained. A very simple example is you have your def formulation for writing a function. You have a lambda. Why bother to use lambda? Yeah, it saves a couple of lines of code, but you can only have one line. You can't have any statements in it. It can only be expressions. Why have list comprehensions when you can just build the list with a for loop? Well, the reason is, oftentimes when you're reading through code, if somebody makes a choice of using a more restricted structure, then it helps the reader because their guesswork for what actually happens behind the scenes, in order for them to kind of pierce the veil of that abstraction, is less. And so one of the reasons why you might choose to use a more restricted part of the data model is not only because you forecast that you don't need keyword arguments or some additional functionality, but you're also subtly broadcasting to the reader that this thing only does so much and only can do so much and only will ever be designed to do so much. And so in the case of property here, you're saying this is something that doesn't need to know any information other than the current state of the object. Whereas call could need much more information that gets passed in, and you may not always be clear about what gets passed in because it could have like a star-star quarks argument there, and so there could be fields that are passed in, parameters that are passed in that are not explicated in the docstring. More fundamentally, however, this guides us to some information about something kind of interesting, which is there is part of the Python object model about how do you look up properties. And so I wanted to do a deep dive into, in the remaining 13 minutes we have, I want to do a deep dive into two parts of the Python object model to show you how much flexibility there is. Fundamentally, what I want you to think about here is that Python is not fundamentally dynamic, it's more operationally dynamic in the sense that somebody has built a model, they've added hook points at specific parts. You can hook into those hook points, but there are going to be gaps whereby there's just not a way to hook into this behavior, or there's a corner case, or there's a wart. And so you'll see that even with getAttr, getAttribute, and get. You may already be familiar with getAttr, we've seen it before. This is what gets hooked when you do a attribute lookup.abc, right? And so you can see here, this getAttr just takes what it's looking up and gives you the string back uppercased. Very simple. Now, you might also be familiar that if this attribute already exists, then getAttr doesn't get called. So you can see getAttr didn't get called. So you may be familiar that as part of that object lookup protocol, there's actually also a getAttribute that gets triggered before you actually check to see if that attribute existed or not. And so if you switch this from getAttr to getAttribute, suddenly that call is intercepted. And so what you can think here is that there's some protocol, there's some steps for how you retrieve an attribute from an object, and you go through those steps, and at each step, somebody has denotated these are hook points. One of them is, before you even look it up, call getAttribute, then look it up normally. If it exists there, return it. Otherwise, call getAttr. And even things like property fit into that, because things like property are implemented using another protocol called the descriptor protocol. What happens is, when you look something up in an object, if you don't see it on the instance, and you don't get it back from getAttr or from getAttribute, but you find it on the class, and the thing that you find on the class has a get method, then you call that get method. So you have yet another hook point. And this is how class method, static method, actually no, that's not a static method it works, but it's how class method, normal methods, and or on all Python functions actually, but class method, normal methods, and property are implemented using this descriptor protocol. And so it's just yet another hook point. Now the reason to go through these, and the reason to go through these quite quickly, is that knowing exactly the details of how this protocol works is less important than knowing that the protocol exists, and knowing that when you're asking a Python object to give you an attribute, there just tend to be certain hook points in that, and having a broad awareness that those hook points exist as part of the design of your system. The details of those hook points are multifaceted, like what does this instance and owner quite mean, and what can we use to employ that? There's quite a lot of detail there, but it's not necessary to know that at a very high level. What's probably most important for most of you to understand as you set out to design production systems is that this exists at all, and how it's designed and structured. Similarly, I want to talk about the object construction protocol. We know that we can construct an object like class T, and then there's an object. But this is actually dynamic code. This isn't C++, this isn't C, this isn't Java. There isn't some bag of bits that represent this class, or in C++, and C, no actual runtime representation of this class, but only some compile time representation to figure out how you can translate pointer accesses into direct offset load operations. This is actually runtime code. And we may be familiar that there's a dis module in Python, and that dis module disassembles code. So if I have a simple piece of code like x plus y and I disassemble it, I can see the Python bytecode. A very brief introduction to it. This is the line number. This is the offset for the bytecode. This is the bytecode. This is the operand. This is the interpretation of the operand. You can see when we add two values, we just call a binary add. And this is how Python works. Underneath the covers, it's running through these bytecodes. It's running these bytecodes. It sees the binary add, and then it dispatches to pi number add or pi object add or whatever. One of those methods to go and figure out what this addition operation actually does. In fact, in the case of binary add, it'll first check to see if they're both Unicode types, and then it'll perform a sequence concatenation as a fast path, and otherwise it'll dispatch to the numeric addition mechanisms, which will then dispatch to either numeric addition or concatenation operations. Now, one interesting thing that you might see is if you try and create a class inside a function and you disassemble that and you look at that, you can see this thing called load build class. Now, if we're running Python 2, which I really suggest most of you do because it's going away soon, so you might as well get just your last few minutes of Python 2 in. It's actually even easier to see. In Python 2, you can see there's a bytecode called build class. And one of the correspondences that we saw very early in this talk was a correspondence between some built-in function, some underscore method that implements that built-in function as part of the vocabulary. There's also another correspondence. For every one of these bytecodes, there's usually, or for many of these bytecodes, there's a correspondence between this and some mechanism that implements that. And so it turns out there's a mechanism that implements how a class is built in Python. There is, in fact, a built-in function in the built-ins called build class. And if you write your own version of it, you hook every class construction in the entire runtime of your program. And so here, if we run this block of code, we'll see when we built this class T, we hooked into this code here, and we got the function that would create T in the name of T. Now, this is not a mechanism that you might be aware of, in part because it is not a surgical mechanism. It is an incredibly broad broadsword, and as a consequence, it's not particularly useful for anything production. It's not used for any sort of business logic. I'll show you why. Let's say we hooked into build class to hook into when classes were constructed. And then we just very innocently imported JSON module and data classes module. This hooks into every class construction in your running program. And so it hooks into a bunch of stuff, and there's very low likelihood you want to hook into all those. So this build class mechanism is there, and it exists. And what it might be useful for is if, for example, you need to modify certain things like memory allocation, or you want to do some debugging, you want to see what classes were constructed, you wanted to notate where classes were constructed when and why, you wanted to do some kind of logging or some kind of automated testing. For example, every time a class is run, maybe you run some test associated with it under some certain debug mode, something like that. But other than that, it's not particularly useful. More useful might be the metaclass mechanism. Now, we don't have enough time to talk about what a metaclass truly is. And I gave a talk about 2 years ago called How to Be a Python blah, 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 expert blah, blah, blah. And it got a lot of hits on YouTube because the title was just provocative enough that people wanted to click on it to either put you down and say, oh, that's so easy, that's not Python expertise, or they were genuinely interested in learning about it. But I would suggest that you might look up that talk if you're interested in what a metaclass truly is. From our perspective here, we'll just talk about a metaclass in terms of the mechanism that it provides. It's just a hook into the object construction process. In other words, when you construct a type here, and you give it a metaclass, there's 2 hook points for how that type is constructed. One's called new and one called init. There's actually one more called call. We won't go into that here. And they're just hook points for when this object is constructed. So if we run this code, we can see as we constructed this T, we got hooks into them. And because we have a hook into the construction of this T, we can do things like modify this. We can add extra fields. We do some fancy things. One fancy thing we might be able to do is we might be able to supply the dictionary that's used for processing the body of that class. And so here, this prepare, which was actually also available in Python 2, gives you the ability to hook into the dictionary that's provided as a namespace for the construction of the body of this class, which may seem very abstract, but you've almost certainly seen something like this before. That's how enum works in the standard library. This auto thing, like what does it do? Well, what's happening is in the enum has a metaclass, which gets inherited. So this components inherits that metaclass. When you inherit that metaclass and you process this code, you're given a dictionary. When that dictionary is filled up, actually I don't know if that's exactly how enum works. But as a dictionary is filled up, you can do whatever magics you want. One of the things that is necessary is in Python 2, you have to provide an ordered dictionary because Python 2 dictionaries are no longer ordered. So you do have to use prepare. That gives you these in ordered, and then you can use the new or the init on the metaclass in order to swap out these auto fields with an actual numerical constant. In Python 3, you use auto. But in Python 2, that's not possible because they didn't add auto to the enum type. But it really only about looks like this in Python. As I said, you provide an ordered dict when you're providing the namespace for executing this class. As you execute this class, you just look for all the items that are auto. And if they're auto items, then you replace them with a numerical value. This is how you can implement this. It's about 15 lines of code to implement some fairly sophisticated functionality. Now, again, there's quite a few details here. And this is also Python 2 code. So get your last bits of Python 2 in before it goes away. But fundamentally, what's important to understand is that as part of building this universe in Python, there are a lot of these hook points in both attribute lookup or object construction that give you the ability to customize how Python does these operations you might take for granted. And so the combination of all of these together are what gives you your own custom object system. This is how most large production systems end up looking like. I don't think we'll have time to go over the example, but in the example I had sketched out a couple of places where you might see that beginning to peek out. Most Python systems start very simple and they don't use any of this functionality, but instead they'll grow towards having their own custom object. There'll be some set pattern for how all the objects are designed, what the objects need to have. They may use mechanisms like init subclass. Init subclass is the replacement for, or is the intended replacement for a wide variety of uses of metaclasses. And an init subclass, what you can do is you can actually do things like you can add in extra keyword arguments to your class definition to define things that should be automatically generated on that class. And so one thing that you could do is you could make this resistor automatically JSON serializable, automatically decodable from JSON, and you could provide guidance for how that's done in the keyword arguments when you derive this thing. Here, I'm just giving it some measure information, so maybe it'll be able to print out nicely what the units are, could do some unit conversion. That might be the use case, but that's what an init subclass is for. Now, the question is, if I don't do this explicitly, am I going to end up doing this implicitly? And in my experience, most large production systems in Python end up creating their own object systems internally, and they end up not using the mechanisms provided to you by Python, and so they end up being both as complicated as all the examples that we've looked at so far, but much harder to understand because all of the mechanisms employed are completely ad hoc. They were just written on as needed. And so the final guidance that I would give you is that it is very valuable to understand the details of how all these hooks work. It's very valuable to understand how the Python object model works because a large production system, not an analytical system, but a production system that has analytical components will eventually evolve in this direction. And if you don't understand all of the things that we've talked about in this session, there's a very high likelihood that the code will be just as messy and just as complex as everything we've seen so far, but even harder to understand because it won't use anything built into language. So I hope you enjoyed that. I think that's all the time that we have for this session. That was Objectionable Content. I'm James Powell. Thank you so much.